Welcome to a tutorial on the 8085, and here we're going to discuss about its RAM structure. Okay, so I'm going to show you a diagram over here. Okay, so there you go. So now this diagram on the left that you can see is actually the RAM structure of the 8085 microprocessor. You see, all types of microprocessors, okay, they have some kind of RAM inside them. Okay, so microprocessors basically they need RAM memory, okay, in order to function as programmable devices. So likewise, the 8085 microprocessor, okay, it also has an amount of inbuilt RAM, okay, within its own structure. I mean, this is all built within the 8085 chip. But the fact is that, well, all these RAM that you can see over here, this entire RAM content of the 8085 microprocessor is just based on 10 registers actually. Okay, so out of these 10 registers, we can basically see that, well, 8 of them are 8-bit registers. Okay, I'm just gonna write that down over here, while just 2 of them are basically 16-bit registers. Okay, so as the diagram on the left basically shows us that we got well, we can see that we have 6 general purpose registers over here, that is B, C, D, E and H, L, which are all 8-bit registers. Okay, and there is one very important register over here known as register A, or the accumulator, where the data needs to be sent into for execution, and the other one, that's flag, where the data conditions, I mean whatever the conditions of the data is, which is basically being stored in the accumulator, are just recorded over there. So apart from that, we have, well, 2 16-bit registers, as I said, the stack pointer and the program counter, which are, well, together known as memory pointer registers. So if I might try and classify the entire registers of the 8085 microprocessor, so this could be done on in a way that I'm just going to point out over here. So registers in a microprocessor can just be, I mean, in the 8085 microprocessor, can just be divided into 2 categories. One would be the general purpose registers, okay, and the other one, okay, so the other one is just going to be known as the special function or purpose registers. Okay, so special purpose or function registers. Okay, so what happens over here is that, well, apart from all the 10 registers that we have seen over here, as I said, the registers B, C, D, E and H, L, they all come under the category of general purpose registers. Okay, so with these general purpose registers, all of them are, well, 8-bit registers actually, as I said. Now we can just store data in these registers temporarily, so we can basically use them for storing 8-bit data, since they are 8-bit registers actually, and this storage is just temporary, only during the time when the program is being executed. Okay, and the data stored in these registers, well, doesn't remain here lifelong. Okay, whenever another different program needs to be executed, the data stored previously in these registers, they're just cleared off just like that. Okay, so this is the general purpose registers that are used for storing data temporarily during program execution. And on the other hand, we have, well, some special function registers. Okay, now they just include the accumulator flag, the stack pointer and program counter registers. So I'm just going to write that down over here. This just consists of register A, or the accumulator register. Okay, and then we have the flag register over here. Okay, and the flag register is also referred to as register F in short. And then we have the program counter, okay, also referred to as PC in short. And finally the stack pointer, also referred to as SP in short. Okay, so the program counter and the stack pointer registers are just 16-bit registers, okay, while the accumulator and the flag registers are 8-bit registers. Okay, so I'm just gonna write that down over here so that you don't have any kind of confusion whatsoever. Okay, so now in this tutorial what I'm gonna do is that, well, we're basically gonna elaborate. Now I just described, well, what the general purpose registers are basically used for. So I'll give you an example on the way, not a problem. But mainly we're going to stress our attention on the accumulator and the flag registers function. Okay, so let's just take a look at how the accumulator functions. Okay, so we're here now. So let's just take up an example, okay, for the ease of your understanding. Let's say we want to add two numbers. Okay, so let's just take up a number, let's say, 3AH, okay, and another number, let's say, what do we take? Okay, 23H, not a problem. So we're going to add these two numbers, okay, that's 3A and 23. And let me just tell you that whenever now if we want to add them manually, then we can just do it just like that. But if we want the microprocessor, that's the 80852, to well, go forward and add these two numbers, then in order to do that or instruct the 8085 microprocessor that way, we need to supply these values as the operand data. Okay, so the 8085 microprocessor will just execute these operands, okay, to produce a corresponding result. Okay, so and this would require to write a program. Okay, so if we basically want the 8085 to execute that, then we'll need to write a program. Okay, and in order to write a program, we have to involve the accumulator register in order to execute this addition process. Okay, so so let's just perform this addition manually and see what the result is. So in order to do that, we need to, well, convert them to their corresponding binary formats. So otherwise it's a bit difficult to realize. So I'm just going to convert them to their binary formats over here. So we're going to get for 3A 0011 and 1010, and for 23 we're going to get 0010 and 0011. Okay, now if we just go forward and add them, okay, so that's what you get. And now we are going to divide it into groups of 4. So for the lower, now this, if we just start from the right, this group of 4 is just a nibble, okay, and is referred to as the one on the right. The group of 4 on the right is just referred to as the lower nibble, and the group of 4 on the left is referred to as the higher nibble. So the lower nibble is equivalent to, so here the lower nibble is basically going to be equivalent to D, okay, in terms of hexadecimal, since these values are hexadecimal. And the higher nibble, okay, I just made a mistake in the higher nibble over here, so this shouldn't be 1, okay, instead it should be 0 that we should get over here. Okay, so kind of don't mind at that. So the higher nibble is going to be equivalent to the hexadecimal 5. Okay, so the addition of these two numbers is going to generate a result of 5DH. Okay, so we're going to get this sort of a result. So in this case, we need to keep certain things in mind while trying to write a suitable program to perform this process using the accumulator. That it's an 8-bit register, we already know that, and the most important fact is that, well, it's a part of the 8085's arithmetic logic unit. Okay, and secondly, the data or the operand data, okay, in the that's being used in the program needs to be stored in the accumulator for execution, and the result of any mathematical or logical operation performed on any kind of operand data is the result I'm talking about is stored in the accumulator itself. And this is basically a default process which is just brought about in the third point. Okay, so what we have to take from over here is that, well, since we are going to execute an addition process, now as the second point says that operand data should be stored in register A, I mean in the accumulator, so we should at least store one of the operand data. It could be either 3A or 23 in the accumulator. Okay, so let's just store 3A in the accumulator. So in order to store 3A in the accumulator, we need to learn an instruction that is known as MVI. Okay, now MVI stands for move immediately. Okay, I should write immediately. Okay, and you're supposed to declare it somewhat this way. You're gonna you write the MVI, okay, and then you just specify the name of the register. So this is gonna be the register where you want to move your data, I mean where you want to load your data, and you just give or give the value of the data over here. So this is going to be the 8-bit data which you want to load in a particular register. So this is just used for loading data. So this is basically used to load data, okay, into register. Alright, so we're going to use this instruction to load data into the accumulator first. So let's just do it this way. So we're going to make two columns over here. That is opcode, okay, and the other one is an operand. So opcode refers to the instruction over here, okay, and operand refers to, well, the data that you're supplying along with the instruction. Okay, so we're going to write here MVI register A, okay, and then give the 8-bit data, which is just since we just chose to store 3A over there, so we're gonna write here 3A. So this is the very first programming code that you're writing, so you should actually congratulate yourself. Okay, so after that we need to again add this particular data, that is 23H, with the data present in the accumulator. So currently what we have is that we have the register A loaded with this data, that is 3AH. Okay, so now in order to add 23H with 3AH stored in the accumulator, we're going to learn another instruction that is just known as ADI. Now ADI is actually known as add immediately to data present in the accumulator register, or the register A, okay, in short. So if we're supposed to use this instruction somewhat this way. We're gonna write here, well, ADI, okay, and give the corresponding data. So we're gonna give an 8-bit data over here. So using this instruction, we can just add any given 8-bit data, so which we are just declaring beside the ADI command. Okay, so this 8-bit data that we are just declaring over here, this 8-bit data is going to be added to the data present in the accumulator right now, that is 3AH. So if we write 23H in place of this 8-bit data, so we can just execute the addition process. Alright, so we're going to do that over here. So ADI, we're going to write here 23H, okay, and then finally stop our program over here. So that just brings an end to our program. So after this program codes just get executed, so A had 3AH stored in it, and now we had added 23H with this 3AH data, and now after the program code gets executed, register A is going to store the result, that is 5DH. So after the program codes get executed, we're going to have 5DH stored in the accumulator. Okay, so this is exactly what the third point says, that the result of any operation performed on operand data are stored in the accumulator by default. So this is actually the result that is being stored in the accumulator, right? And now in this addition process, we see that there is no carry bit being generated, which can happen in an 8-bit addition process. Okay, so now what I'm gonna move on to is basically the flag register. So this flag register, as I said before, is used to test data conditions. Now the data that is present in the accumulator right now is 5DH. Now let's see how this data affects the condition of the flag register. So here we are with the flag register. Okay, so now this box that you can see over here, now you can see that it'll basically, well, has 8 cells. So this is actually the flag register, or quite close to what we can, well, picturize the flag register as, well, an array of 8 cells. Okay, so this is an 8-bit register. You can just, well, think of this entire thing as the flag register, which is of course an 8-bit register, and these symbols that just lie below each of the bit positions, well, these bits are referred to as the flag bits. Okay, so these bits are D7, 6, 4, then D2 and D0, so which has certain special meaning over here. They are just referred to as the corresponding flag bit. So actually we can just refer to any of the cells over here starting from D0 to D7, any of them as flag bits. But these flag bits that I'm talking about over here are the special ones that are actually used to test the data conditions. So it is these bits that I'm just talking about over here. Okay, so now let me just point out a few things about the flag register in short. Well, as we know, it's basically an 8-bit register, as I just pointed out over here, and like the accumulator, it is also a part of the ALU that helps in deciding certain logic functions and all. Okay, the next we got the point where it says that the flag register is basically used to test the condition or the status of the data currently stored in the accumulator, as I just pointed out a little while ago, and that just happens after an instruction is executed. So we got an idea over here that as soon as, like say for example in this edition, as soon as the ADI instruction gets executed, okay, the result gets stored in the accumulator register, as you can see over here. Now as soon as the result gets stored in the accumulator, okay, the flag bits that I've just talked about over here, they get affected, okay, and these flag bits are either set or reset depending upon whether the data present in the accumulator satisfies certain condition. So I'm just going to elaborate about the flag bits. So let's just start with bit D7, which is just referred to as S. Now S stands for sign bit. Okay, so this bit gets set to logic 1 value if the D7th bit of the result in the accumulator is also logic 1. So if we can just summarize it over here, if D7th bit of the result in accumulator equal to 1, then sign bit is also equal to 1. So let's do one thing. Let's just take up an example. Let's take up this addition example over here, and as I said, we're gonna be actually seeing how this result affects the flag bits. So let's just put this 5DH, that's the result, in the binary format. So let's just do it that way. So for 5 we're gonna get 0 1 0 1, okay, and for D we're gonna get 1 1 0 1. Okay, there you go. So now as you can see, starting from the right, this is basically bit D0, this is D1, D2, 3, 4, 5, 6, and finally D7. So this binary number, okay, so this is actually the 8-bit data represented in this binary format, and with this binary notation we're gonna see how the flag bits just get affected. Okay, so now we can see here the bit D7 is 0. So as I said, the sign bit for this result, that is 5D in the accumulator, this result is actually not going to set the sign bit at all. So here the bit D7 would remain reset, and that is, it'll have a logic 0 value. Okay, so next we have the bit D6, which is referred to as the 0 bit. Okay, so this is just referred to as the 0 bit. Now the 0 bit is actually set if the entire result in the accumulator is 0. So if result in accumulator is actually 00H, then we can say that bit 0, okay, then Z will be equal to 1. So then Z will be set. Okay, now we can see that the result in the accumulator is not 00H. So now the result being a non-zero quantity, so we can understand that the 0 bit over here also remains reset. Okay, so we put a logic 0 value in place of the D6th bit. Okay, now next we come to D4th, that is AC. Now here AC actually stands for auxiliary carry. Okay, so this is auxiliary carry. Alright, so in this auxiliary carry bit, bit D4 is actually set if we have a carry from the D3 to D4 bit positions. Like for example, when we were adding the numbers, that is 3A and 23H, if we had a carry from, let's say we just put the positions once again, so the D0, 1, then 2, and then 3. So this is D4, D5, D6, and finally D7. So if we basically have a carry from the bit D3 to D4, then only the auxiliary carry bit would be set. So if carry from D3 to D4, okay, then AC flag will be set. Okay, so we can, if we just monitor this process, since we're just doing it for this result over here, so we're going to monitor for this process in the addition of these two data. Okay, now if you check this addition process more closely, then you'll see that there is actually, well, no carry from from the bit positions D3 to D4. So we can say that, well, no carry from D3 bit position to D4. Okay, now this is gonna mean only one thing, that the auxiliary carry bit of the flag register would only be reset. So it's also going to remain at the logic 0 level. Finally, we also have the bit D2 that just stands or labeled as P over here. So the P actually stands for parity. Now the parity flag bit, now this is basically set, okay, only if the result in the accumulator has an even number of ones. So if I might write the condition over here, so if result has even number of ones, okay, even number of logic ones, okay, then only the parity bit flag, the parity bit flag bit would basically be set to logic 1 level. So let's check our result. Okay, so this is the binary format. So we can see that it has 1, 2, 3, 4, 5. Oh, sorry, we have an odd number of logic 1s. Okay, so it's hard to be disappointed again that the flag, the parity flag bit is also going to be reset over here since the number of ones is not even. So once again we put a logic 0 level at the bit position D2. And finally we need to check for carry. Now the carry bit, this particular the bit D0 known as CY, it actually stands for carry. Okay, so this is actually the carry bit. Okay, now this carry bit is set only if we'd have a carry bit being generated as a result of addition. Now we see that there is no carry, so this addition involves no carry. Okay, so finally we can see that, well, now this carry bit will be set. Now CY will be equal to 1 if carry bit is generated. Okay, if carry generated. Now we can see that our addition doesn't generate any carry as such. So once again, the bit position D0 of the flag register, that's the carry bit, would also remain at the logic 0 voltage level. Okay, so we can see that, well, this addition process, well, doesn't actually affect the flag bit in any way, or rather affects it in a way so that all of the important flag bits that just test the data conditions remain at the logic 0 level. Okay, so this was just a random example, so you could just try out some more examples on your own and test how the flag bits would just be affected if the data's could be just changed to some different value. Okay, so this was just an example to illustrate how the flag bit is affected by the data present in the accumulator. Okay, so with that we just come to the end of this tutorial, and we're going to meet you next in the forthcoming one. So till then, it's just going to be a short goodbye for now, and thanks for watching.